Okay, thanks very much for inviting me to give the BSA Christmas special. Like most things we watch over Christmas, this one's a repeat. It was originally given as a talk to the British Society of Audiology back in October 2012. However, although it's aimed at, or rather developed with an audiological or hearing science audience in mind, it's applicable, I think, to a wide range of scientific endeavours. So we're going to start off with science. Don't you love it? And of course, as we all know, science relies on both quite intense statistical and logical rigour, and also in terms of ruling out alternative explanations for one's findings. And it really is, I think, this that separates us from the savages. And by savages, I mean those other approaches to understanding the world and to alleviating illness that have been proposed from time to time and which don't necessarily welcome critical appraisal. One of the problems, however, is that scientists keep making mistakes, and actually the same ones keep popping up. And these mistakes range from the simple to the subtle and are surprisingly common. So I'm going to start off with a few health warnings. One of them is I'm not a statistician, which has got some good and bad things about it. So on the negative side, you're not going to be treated to some very sophisticated statistical arguments. But on the other side, you're not going to be treated to too many sophisticated statistical arguments. There are no equations. And those of you who are quite well versed in stats will have the opportunity to shout at the screen and feel pleased with yourself that the speaker isn't quite as sophisticated as you are. Some of the examples which I'll be presenting have been discussed at length in dedicated articles, mostly in the neuroscience rather than the clinical field. And the examples which I portray in this talk are entirely fictitious and bear no relationship to actual studies, living or dead. Well, actually no direct relationship, because obviously I've got to base my examples on some things which happened in real life. And those scientists were harmed during the making of this talk. So I'm going to describe my main points in the light of a series of books which were originally available in the 1960s and 70s in the United Kingdom, which were known as the I Spy books, which have been recently relaunched in the last few years. So in the I Spy books, children get points for identifying certain items, and you get more points the rarer the item. So, for example, in the I Spy book at the airport, you only get 5 points for spotting a baggage trolley, but you get 15 points if you get to witness a body search. And what I like about this particular example is you get double the points if this actually happens to you. So this seems to be a way of encouraging small children to smuggle metal objects through the security barriers at major international airports. Another thing about this example is that I'm reminded of a very distinguished and well-respected colleague of mine who 50 years ago, when he was a small boy, lied about some of the things which he had or actually hadn't seen in order to be able to fill his book up and get the ticket and send it off to Big Chief I Spy, where he would get an extra feather for his headband. And all I can say is that 50 years later, he still feels guilty about this. So if you're ever contemplating scientific fraud, I would strongly argue against it. So I'm going to start off with what I think is perhaps the most common error. So this is the I Spy equivalent of going to the airport and spotting a plane. And it's one which seems to crop up everywhere. So in this fictitious example, it's predicted that a new signal processing strategy will improve speech perception by cochlear implant listeners, and the listeners will be able to learn the cues provided by this new strategy. So 10 users were tested on the new strategy several times over a period of a few months, and they show a significant improvement on a speech perception test. And to control for general learning effects, because the authors aren't completely stupid, they tested another group for 4 months using the old strategy, and in this control group, the improvement was not statistically significant, so it was only significant up here for the experimental group. And it's therefore concluded that to improve speech perception, listeners should be provided with this new processing strategy. So the problem here is that it could be that the improvement only just reaches significance with one group. For example, you might get a p-value of 0.049 and just fails to reach significance for the other. For example, with p equals 0.051. But this does not, of course, mean that the strategies differ. So what we're really doing here is comparing the improvement in one group here, shown in red, with improvement shown in another group here, shown in blue for the control group. But it could even be that the non-significant difference is actually bigger, because what we're really doing is comparing the size of this difference to the standard error, and so we could actually have a larger, or standard deviation, I beg your pardon, so we could actually have a larger difference here for the case which is non-significant, and a smaller difference for the one which is significant. So what's clearly important here is it's absolutely necessary to show a times frequency interaction rather than showing that one effect is significant and the other one isn't. And this error is is very common indeed. There was a paper by Neuvenhuis in 2011 which reviewed papers in some top neuroscience journals such as Nature and Science and Nature Neuroscience, and found that around about half of them used the incorrect method. Now, that's all very well, but it's quite easy to think, well, that's the sort of thing which happens in these sort of flash journals where people's promotion to some higher professorial level depends on getting this high impact publication. But these things even happen in top auditory journals, which are renowned for their experimental rigor. So here's an example from the paper studying the slopes of the psychometric functions, that is sensitivity as a function of sound level, for detecting some tone pips in normal hearing and hearing impaired listeners. And in this case, the authors say, well, the mean slopes for the normal listeners do not differ significantly from unity in any of the three stimulus conditions, but for the hearing impaired listeners, the slopes do differ significantly from unity. So usually, throughout this talk, what I'm going to do is to protect the innocent by anonymizing any examples which I give. But in this case, I feel it's probably okay to just own up that this was me back in 1990. So this is more than 20 years ago. And again, I still feel bad about it. However, on the plus side, as you remember from my earlier example, you do get double points if it happens to you. So I get 10 points for this one. Okay, here's another example, which is perhaps a little bit harder to spot. And in this case, some researchers have noticed that older people seem to have difficulty with foreign accents, and suggest this is due to the auditory system becoming less flexible as it ages. So there are two groups of listeners, some younger and older listeners, who were tested on speech materials pronounced either with a British or a Dutch accent. And in this case, they actually do the correct thing in a sense, as they do an analysis variance and show a significant interaction between the age and group, because the difference in percent correct score between the British and the Dutch accent is larger for the older group than it is for the younger group. So it's concluded that older listeners are indeed particularly impaired at listening to foreign accents, and that this supports the reduced flexibility hypothesis. So the problem here is that there's a genuine interaction, but the two groups also differ in overall performance. So the real big question is the difference between 40 and 60% shown here really bigger than that between 70 and 80%? And we know that percent correct is not linearly related to the amount of information one hears. So, for example, if you had an implant processing strategy which only conveyed really high frequency information, and you listen to the word ash, then you would get 0%. And if you had another strategy which only conveyed very low frequency information, you would also only hear 0%, but get 0% correct because you'd only hear the rather than the sh in this latter case. But obviously, when we combine these two things together, you get 100%, and we know that 2 times 0 doesn't equal to 100. And more specifically, there are lots of different response measures, such as D prime or oxide transforms to percent correct, which are commonly used to transform percent correct data for some good reasons. And these, are not linearly related to percent correct. So there are a number of solutions, but the simplest one here is to somehow equate performance in the two groups in one of the conditions. So, for example, one could repeat the experiments with some younger listeners who were tested in a noise background. So we could bring down the overall level of performance to that, similar to that in the older listeners, and then see whether we still get a smaller difference in percent correct. So some bonus points here, 20 points for your I Spy book. We know that many the basic logic underlying fMRI experiments is to estimate neural activity from the bold response. And it's common to subtract the bold response into conditions, for example, for speech versus noise or sound versus silence. And a typical conclusion might be that the response to speech relative to the noise baseline is larger in region A than in region B. And the conclusion might then be that region A is more involved in speech processing. But of course, it might be that the baseline response to the noise might be different in the two regions. So it's kind of analogous to the same problem we had with the behavioural experiment, which I just described. So this comparison will really only be valid if both of the following relationships are linear. First of all, the amount of information processing which is going on in the brain is linearly related to the amount of neural activity, some firing rate or whatever you like. And secondly, that the neuron activity is linearly related to the bold response, and it's clearly not necessarily the case that either of these two conditions will hold. So perhaps the probably best way to overcome this is design an experiment that produces a crossing interaction, or sometimes called a crossover interaction. So here's a study from Heinrich et al., who used two stimuli, one I'll call stimulus A, which sounded vowel-like, but only by virtue of an auditory illusion, in fact something called the continuity illusion. And the stimulus B, which didn't sound like a vowel and didn't sound like speech, but sounded interrupted. And the prediction was that stimulus A would produce more activity in a speech region than stimulus B, but the opposite would be true in the primary auditory region, which might be more sensitive to these interruptions. And indeed, that's what they found. So we can see the vowel sounding stimulus produce more activity in the speech region, but less in the primary auditory region. So what's nice about that is that you can perform whatever sort of nonlinear transform you like to this ordinate, but you'll still be left with this basic result that one is higher than the other here, and the opposite is the case in the second case. However, there is still a sort of a bonus thing we need to worry about. So 20 points if you spot this. And that is that this conclusion would have been entirely invalid if, rather than predicting in advance what these two regions were, the authors had just searched throughout the brain to look for one region which showed the largest response to speech and another region which showed the largest response to the non-speech sound, and then demonstrated the interaction, because that's kind of cherry picking, or as we say technically in the statistics world, cheating. Okay, so here's one of my favourites. Cheers. And I should emphasise that this is entirely fictitious. As part of the Rewind learning programme, some children within a range of reading scores underwent 3 weeks of training listening to slow down speech. So the hypothesis here is that listening to slow down speech will help poor readers. And indeed, children who perform more poorly to begin with showed the greatest improvement. So I'm showing here the improvement, so the difference between the final and the initial score as a function of the initial score. And what we can see is there's a nice significant negative correlation. It's minus 0.5, statistically significant between the initial score and the improvements observed. And the authors concluded that this Rewind program is especially beneficial for poor readers. However, the problem can be thought of as described in a number of ways. I like the term double dipping. In this example, the subject tested twice at times A and times B. So the initial score is A, and the improvement is B minus A. So of course, these two things are going to correlate negatively. In fact, by chance, they'll correlate negatively with a value of minus 0.5 because they both got A in them. This one's got A and this one's got minus A in it. So you'll just get this with just random data. And this problem just crops up all the time in different guises. In a lecture given a couple of years ago to the BSA, Professor Brian Moore gave an example where a group of listeners switched to a new hearing aid, and that those who did poorly with the original aid improved, and those who did well got worse. One could measure an evoked potential before and after a sound, and showed that the increase in neural response to the sound is larger for subjects where the baseline activity is low. Or even if we want to measure the dynamic range, which is smaller, and find that this is smaller in cases where the thresholds are high. And the reason for that is, of course, the dynamic range is the difference between the loudest sound the subject can bear and the threshold. So this is clearly going to correlate negatively with threshold. So all of these examples have cropped up in real papers and presentations, which I've seen sometimes from quite prestigious speakers. There are a number of solutions. Perhaps one straightforward solution is to correlate the improvement, that is B minus A, not with the original score, but with the average of the two scores. So that will work. Or one could define your initial performance using half of the trials and use the other half for the improvement. And again, that would overcome the problem of this sort of double dipping of having the same thing in the two halves of the correlation. Okay, here's a fictional neuroimaging study, or imaging study, which you get 10 points for. So again, not particularly hard to spot, but pretty much ubiquitous. So in this case, there's a study which is performed to determine whether extended practice can affect both the structure and the function of motor cortex. Three groups of subjects took part. One of them are professional tiddlywink players with at least 10 years of experience. Another group are people who've undergone 1 year of training at the National Tiddlywink Academy. And the third are people with no tiddlywink experience. So if you don't know what tiddlywinks is, it's a game where you have to flick counters, one counter with another, in the hope that the second counter will leap up into the air and land into a small pot. In this study, structural MRI scans have revealed that the thumb area and the left motor cortex is larger in the professional tiddlywinkers than in the other two groups. And there's an fMRI experiment which shows greater activation in the same area during a dummy tiddlywink task where the person's sort of flicking their fingers compared to wiggling their toes. And that's true in all three groups. But this increase is significantly larger in the professional tiddlywink players than in the other two groups. And so the researchers conclude that extended practice can indeed affect both the structure and function of motor cortex. Well, the problem here is one of the direction of causality. So here's one of my favourite ex-gay CD cartoons, where someone's saying, oh, another huge study found no evidence that cell phones cause cancer. You know, what were they thinking of? And the man in the hat says, well, I think they just got it backwards. And this is a plot of the total incidence of cancer increasing in the United States as a function of time. And it's clearly leading that to cell phones. And so he's concluded that, in fact, cancer causes cell phones. So we know that's ridiculous, and we also know there aren't really actually real studies on tiddlywink players. But there are just loads of studies about musicians which show differences in white matter, improved ability of the brainstem to track pitch contours, or larger or more synchronized neural responses. But we don't really know from the vast majority of these studies whether that's because something's happened to the musicians as a function of performing their musical training, or whether it's simply that people with different brains do different types of pastimes. So the true solution here is to perform a longitudinal study. Okay. On to another 10-pointer. Oranges are not the only fruit. So this is the case where the authors of a recent paper conclude that a fictional region of the brain called the dorsolateral homunculum is involved in the processing of complex odours. And they perform an fMRI study in which participants are required to identify the smell of bananas in a mixture of other odours. And they find greater activation in those who successfully perform the task than those who didn't. And that's shown by a significant correlation between activation in the dorsolateral homunculum and percent correct on the task. Furthermore, the same study shows that for a given participant, the bold response in this area is greater on successful than on unsuccessful trials. So it's greater when the person successfully identifies the odour. And both of the above effects are greatly reduced when participants perform a demanding competing task. And similar findings are obtained when the participants are required to identify the smell of oranges. So it's clearly not a banana-specific finding. So the issue here is, again, just the direction of causality. So here it might be that the bold response might reflect the result of performing the task correctly, rather than the processing needed to perform the task. So, for example, if your subject in this experiment were Alfie here, and you presented a sensor just about Here, you'd probably get the same results. In other words, you might get a pattern of results which reflected the person's success in performing the task rather than the processes needed in order to do the task in the first place. So there's not been any studies so far on sniffing oranges, but there have been plenty of studies on speech and language processing and, for example, in learning, where it's not clear whether the regions which are revealed reflect the learning process itself or the result of having learned to understand something. Another, one more 10.1, so these are all medium difficulty. This is about a study which measures speech perception and the discrimination of asymmetric modulators applied to electric pulse trains in a cochlear implant listener. So here's what we might call a damped modulator shape. It goes up and then decays slowly. And here's one which is often known as ramped, so it's increasing over time. So the listeners have to discriminate between these two stimuli. Performance on these two tasks correlate highly significantly. And so it's concluded that cochlear implant processors should then be carefully designed so as to preserve these modulation asymmetries. So the problem here is that there are really two sources of variance in the data. So there are a number of factors which might predict the speech scores and might relate to differences that can be altered for a given subject, and that would be really interesting. So as the authors conclude, maybe that you could change the cochlear implant strategy or the fitting accuracy. But there are also differences which are across subjects which can't be altered and which reflect between subject differences, such as the age or IQ or the number of surviving neurons. And we know particularly in the cochlear implant field that lots of things vary across subjects, and I think that's true generally, that people who are less deaf or smarter tend to do better on a range of tests than people who are more deaf or not so smart. And it's clearly important not to confound these two sources of variance. And I can illustrate this with a screenshot from a web page which allows one to calculate one's chances of getting a heart attack or a stroke over the next 10 years. And the example I've given you here is for a 53-year-old man living in Cambridge. And what you can see is there are a number of things which you can enter into the calculation which will allow the algorithm to determine what your risk is. So a number of these things are things which you can control. So this is something to do with one's blood pressure. This is to do with the amount of and different types of cholesterol in one's blood. And you might not be able to change your height, but you could probably change your weight. And so it's probably true that if I were wanted to reduce my chances, I could perhaps do something to lower my cholesterol level or blood pressure, perhaps by not getting so excited and het up about scientific errors. But you could also, according to this algorithm, change the answer simply by moving house. So I could change my postcode and move to Scotland or to the West Country. But clearly, if I did that, then it wouldn't be the case that by the time I'd unpack my bags, my chances of a heart attack would have suddenly changed substantially. So in a similar vein, here's another study which measures gap detection and this modulation discrimination task for pulse trains presented to 6 different electrodes for each of 10 cochlear implant users. So here we have 60 points in the correlation, 10 users and 6 electrodes, and we get a highly significant result. So the authors conclude that performance in the 2 tasks is mediated by similar mechanisms, and that the ability to discriminate asymmetric pulse shapes depends on the same fine timing cues used to detect brief temporal gaps. So this is again the problem with 2 sources of variance, and in this case it's within subject variance and between subject variance again. So basically either of the 2 following may be true. It could be that subjects who are good at one task are good at another, which I've already argued is pretty boring. Or it could be that for a given subject, the electrodes that yield good performance on one task do so in another as well. And that might be something interesting. It might tell you something about the fact that these tasks do have something in common. You might even decide to perhaps reprogram your implant, perhaps to turn off some of the electrodes which were giving poor performance in both tasks. So what I've done here to illustrate this is I've just replotted the same data, but with the data for each subject in a different colour. And I've now just shown you the best fitting lines to the data for a few individual subjects. So clearly what's happening is that these lines don't have a positive slope. The slopes are pretty close to zero. And so really it's the boring explanation which is true. This is all just due to differences across subjects. But fortunately there are some pretty straightforward statistical methods one can use in this case to perform an analysis of covariance and put the dependent variable as your gap detection, for example, the subject as a fixed factor, and put your modulation discrimination as a covariate. That's about as close as I get to very specific technical advice, by the way. Okay, this one here is called All Right Madook, in honour of the fact that I originally gave this talk in the East Midlands. It's the sort of thing one hears when one gets into the taxi in Nottingham. So here's an example where auditory brainstem responses are measured to a series of clicks to subjects with either Glaswegian or West Country accents. And the authors find that the latency of wave 3 of the ABR is significantly shorter in the Glaswegians. In another example, there's an MEG study which measures the response to noise bursts in people with East Midlands or London accents. And they model the response using two dipoles, one in each hemisphere, and the amplitude of the M100 component, something with a latency of 100 milliseconds or so, of the left hemisphere response is significantly larger for the Londoners. And the third example comes from something called the frequency following response, which is a way of measuring phase-locked activity in the human brainstem using scalp electrodes. And these authors measure the response to a consonant vowel syllable in subjects with either a Welsh or a Geordie accent. And there's a distortion product in the frequency spectrum of this response, with a frequency equal to the fundamental frequency or the pitch of the vowel, which has a larger signal-to-noise ratio in the Welsh than in the Geordie group. So in all of these cases, the authors are concluding that there's something happening specific to people with different accents processing sounds in some kind of different way. So the problem here is one of multiple comparisons. Now, the issue of correcting for multiple comparisons for the independent variable is something which pretty much anybody who's got at least this far in my talk, and who's got the stamina to listen to me wittering on about half an hour or so, will understand and would never in a million years make. So the example here is from yet another XKCD cartoons, where somebody runs up to a scientist and says, jelly beans cause acne. And the scientist goes away and does a test and finds that it's not significant. And then the person says, but I hear it's only a certain colour of jelly beans which cause acne. And so the scientist goes around testing each of the different coloured beans individually and finds that in each case the p-value is greater than 0.05, and there's no evidence that yellow, green, or the yellow or purple or blue jelly beans cause acne. And somewhere around about here, they say, we found evidence that green jelly beans cause acne because p is less than 0.05, and the person shouts out, whoa, and the scientist has got to stop playing Minecraft. And here's the conclusion. So, as I said, this is so obvious, it's in a cartoon. Nobody would make this mistake with the independent variable. But plenty of people make the mistake all the time with the dependent variable. So, for example, in an ABR experiment, there are at least 3 waves which are commonly reported, waves 1, 3, and 5. Of course, there's 2 and 4, they're less popular. But there's an amplitude and a latency for each, so there are actually 6 things which might show a difference. In the MEG response to a noise burst can be broken down into components with latencies of 30, 50, 100, 150, 200, and 400 components, and one could examine the amplitude or the latency of each of these in the left hemisphere or the right hemisphere or both hemispheres comparison average. Someone's got a fair amount of choice. And in the frequency following response, this is, there's even more room for manoeuvre. So the responses are usually measured with stimuli in alternating polarity. So in one presentation, every other presentation, the waveform will be inverted. And the waveforms from the 2 polarities can either be subtracted or summed. And For each of these, one can either measure the amplitude or the latency or the stimulus-response correlation of the whole waveform, or we can measure the spectrum and examine the distortion product at the fundamental frequency and define this as either the amplitude or the signal-to-noise ratio, or something called the phase-locked vector. Or we can measure the autocorrelation, and again measure the amplitude at the peak at the period of the waveform, either raw or relative to the other peaks. So basically, again, there's lots of things to choose from here. So it's not, it's rather like the jelly bean problem, except with a dependent rather than with the independent variable. This happens not just in physiological studies, though. For example, in a behavioural study, one might measure the effects of training, and there might be a number of dependent variables, including tests of memory, hearing, vigilance, etc. And again, one has to be careful not to cherry pick the one factor which produces the significant result. And these effects can be quite large. So there's a paper by Simmons et al. Published in 2011, which showed that with just two dependent variables correlated with each other by 0.5, the chance of the false positive increased from 5% to 9.5%. And rather interestingly, this false positive issue is dealt rigorously with in fMRI experiments. So it's kind of generally overlooked in experiments with evoked potentials. But there's a now famous experiment by Bennett et al. Who measured the response of the brain to stimuli with different emotional content, and deliberately did not, to illustrate the problem, deliberately did not correlate for the fact that there's millions and millions of voxels from which they could record, and did find a significant activation. But the punchline was that, or the twist was that this was clearly fictitious because the subject was not only a salmon, but it was actually dead at the time of scanning. And perhaps as a result of their genius, they were awarded the Ig Nobel Prize for this research in 2012. That's kind of breaking news. So here's a super one, which is a bonus of 50 points. This is basically because I don't really know the answer to it. So then I think the answers are really up for grabs. So what should we do? I think we shouldn't require some experimenters to perform Bonferroni correction, i.e. to correct for every possible waveform component in an EEG wave, for example. And that's because the components will at least be partially correlated with each other. And of course, if they're all measuring the same thing, then you're not getting lots of different bites of the cherry. You're just getting one bite. And of course, there are too many of them. There are lots of frequency or time regions in which one could look. And it might be unrealistic to say to somebody, well, just because your recording window is left open for perhaps 200 or 300 milliseconds, do we really expect you to control for responses which are perhaps much later than those which you're really looking for? So I think there are a few sort of rules of thumb which one can use. So I think if there's a clear a priori hypothesis as to what waveform, which component one should be looking at, that should lend some confidence. And secondly, if the authors have published similar data addressing a related question using exactly the same measure, and I do use the term exactly here, and I think one should be suspicious if the response measure changes from article to article from the same research group. Our conservative approach, if we don't, because at the beginning, as scientists, we may not really know what we're looking for. Might be a bit of a fishing expedition. So a very conservative approach would be to decide, basically to look at the first half of your data to see what looks interesting and decide what your measure of interest is going to do. And then define a very, very precise hypothesis based on the first half of your data, and then just test using the second half. I think there's an alternative approach suggested by Professor Mark Haggard, which is essentially to perform a factor analysis on which components and measures co-vary across subjects. Basically assume that these guys are measuring pretty much the same thing, and then average measures within each factor. And that gives you the advantage of, first of all, perhaps increasing the reliability of the thing you're measuring, And secondly, you end up with perhaps only 3 or 4 things which you can then bonferroni correct for. And I would say I think there are some more sophisticated suggestions and methods out there. And unfortunately, this is what happens to my head when I try and figure them out. So the examples I've given so far are really in the category of basic statistical or logical errors, which it's fairly easy to spot. If you read the paper, you would be able to decide whether or not there was a problem. But I think there are a number of other sort of invisible problems out there, which I think, as scientists, we're all tempted to fall into. So this one in particular is that what happens is you may do an experiment, you've got this really brilliant idea, you run the experiment and it doesn't work, you don't get any significant effect. So, being a fairly bright, creative person, you think about what you've done wrong and you realise, actually, you should have probably changed the stimuli or used different stimuli or given different instructions to the subject or controlled for some other possible strategy. So you repeat the experiment and it's sort of a little bit encouraging, but it's still not significant. So you go away and you think really carefully. And then you realise that, I should have done something else. So you run the experiment again, and lo and behold, you get this nice predicted highly significant result, and you go away congratulating yourself on your sort of experimental skills. And indeed, that might be the case, but you have to bear in mind that you've now done 3 experiments rather than 1, and you've only got a significance effect, which you probably only tested, based on only as if you'd only done the 3rd experiment. When one reads the paper, it may well be the case that other people just won't be able to know about that because you're not going to describe the 2 experiments which didn't work. Another flaw is when one thinks, well, I've run 8 subjects on this experiment, or I've tested subjects a certain number of times, and it's not quite significant, so I'll just run a few more observations. Well, in a sense, that's okay, as long as you're very aware of what you're doing, but Simmons et al. Showed an example where there were 20 observations per cell in an experiment, and they added 10 more observations and showed that there was an increased chance of the false positive from 5% to 7.7%. And if you have combined this with having two dependent variables, this increases to 14.4%. And if you're really mean and if you're really sneaky and just test, keep adding observations and wait for the significance level to drop below 0.05, then you get a chance of your false positive of 22%. So I'm not saying that if you do run an experiment with that you always have to decide in advance to run a very, very large number of subjects. But one thing I think which is probably valid is to say, well, I'm going to run 16 subjects on this experiment no matter what, but I can stop. I'm going to look to see how I'm doing after 8 subjects, and if I don't get a significant effect, then I'm going to stop. Okay, that reduces, leads to a bit of underreporting of non-significant effects, but at least it means that you're not likely to be reporting an effect as significant when it isn't. Finally, I'd like to talk in general terms about something which I call the Ford-Anglia effect. So this was motivated by, when I was a teenager, a fellow youth in my school was always messing around with his beat-up Ford-Anglia, and he'd always come in the next day with some really implausible claims, such as, I got my Ford-Anglia up to 110 miles an hour on the motorway last night. So to analyse what's happening here, my erstwhile schoolmate chum had a hypothesis which he could make his car go faster. He had an intervention, which was random tinkering in his parents' garage. And there was a test, which was in the motorway, presumably at the dead of night. And there was an observation, which the speedometer reads 110 miles an hour. So he reaches the conclusion, which is, importantly, the conclusion which he really wanted to make all along, which is that he can make his car go faster than it did when it was new, and faster even than performance cars of the time. And this must be contrasted with the more perhaps plausible hypothesis that, like everything else in his car, the speedometer's just stuffed. So this happens in real science all the time. That is where authors have a hypothesis which they would really like to be true. They collect data which are consistent with the hypothesis. They therefore conclude the hypothesis is true, but don't think of all the myriad more mundane observations or explanations, I beg your pardon. So here's an example from two separate studies cited on two different cochlear implant manufacturers' websites. And they're both comparing a new speech processing strategy to the standard. So the subjects are first tested on the standard strategy, and then they're tested immediately on the new strategy. And they find no difference. So they then give the subjects a few more tests on the new strategy over perhaps a period of a few months. And then after they've been tested 5 or 6 times, maybe, they find that the new strategy is now better than the standard. Hooray! But they then go back to retest the standard strategy, and now this is also better than the original score with the same strategy, and is now not significantly different from the new strategy. So perhaps you and I would think, oh well, yeah, that's slightly disappointing. Clearly what's happened is that the subjects have just learnt something about the speech cues, about the speech test which they're doing. They've learned something about the materials, they're learning to attend more during the speech task, and that's why they get better. But what the authors conclude is not that. So here are the 2 quotes from these papers. One of them says, in addition, experience with strategy A seems to enable subjects to then also benefit from the standard strategy. Or another paper, it said the subjects may be able to utilise cues in strategy B that they're now able to recognise in the standard strategy. So in other words, these new strategies are so good you don't even have to have them installed on your device. It's just magic. To be fair, in one of these studies, the authors went back and tested a group of subjects who were just given the standard strategy and were given lots of practice. And then, although there was an improvement, that was not statistically significant, unlike the significant improvement they did find for the first strategy. But hopefully, if you've been paying attention, this is just falling into one of the very first flaw which I described in the talk, which is arguing that because one thing's significant and the other one isn't, that they are actually different from each other. So I've got some further reading. Neuvenhuis is the paper which summarised the number of papers making this problem with the interactions, or failing to test interactions significantly. There's another paper by Gelman and Stern showing that it's not just the case that you might have 0.051 in one condition, 0.049 in another, and them not to be different from each other. But you could even have something which is highly significant at p less than 0.001 and still not be statistically different from something which is not significant at all. Simmons et al. Is the nice paper showing the problems of, for example, running subjects or until you get the answer you want, or having more than one dependent variable. Bennett et al. Is the award-winning paper on the dead salmon, and there's a paper by Fiedler et al. Which addresses a slightly different problem, which is the type of error where actually the problem isn't statistical. If you repeated the experiment and did exactly the same analysis, you'd still get a significant result, but where the stimuli have been just carefully honed down, so that essentially what the person is doing is using only the very, very small subset of stimuli and subset of methods and subject group and selection criteria, which will lead to a significant effect, but that it just doesn't generalise to anything else, and it's not therefore generalisable to the real world questions which you think you're trying to answer. So to summarise, apart from me having another glass of water, scientists are highly motivated and we are trained to see patterns in data, and this is a good thing. That's why we do science. However, it's easy for us to root around in a complex data set and then get excited over interesting findings, which are really perhaps result more of our creativity than on the underlying reality. So most scientists, and nearly all scientists, everyone I know, is extremely honest, but I do think that scientists differ in how tough they are on themselves and how carefully they go back and check to see whether they've fallen into one of these traps and perhaps fooling themselves. It's easy to trust findings when obviously these obvious statistical errors which I've described are absent, when the significance level is high. So, for example, if you think there are 6 dependent variables instead of 1, but the finding is significant at the level of p less than 0.00001, then I think the authors are going to be on safe ground, because even if you did correct everything, the result would still be valid. If exactly the same papers, dependent variables are used in multiple papers from the same lab, or it's obvious a priori what the test should be. Crossing interactions are a good way of ruling out explanations based on nonlinear transforms between the thing you're trying to measure and your dependent variable, such as percent correct, and of course where the direction of causality is addressed. And the good news is, of course, that most problems are easy to spot. But I would like to spend a minute just thinking about what one should do when one does spot them. Either when you see a presenter giving a talk, or you're reviewing a paper for a journal, or you're the editor of a journal, and you spot one of these errors. And I think it's very important to point them out gently, but in a dispassionate way, but one has to point them out, because I think otherwise it's not fair on the presenter, who may not be aware of the problem and will continue to fool themselves and maybe pursuing an area of research which has actually got no basis. It's not fair to other members of the audience, particularly those who might be making clinical or purchasing decisions based on scientific conclusions which might not be valid. And it's not, in the end, fair on patients, who are the ones who will suffer or benefit from the results of those conditions, those conclusions or those clinical decisions. So I think one should do this even if it gets a bit boring, and I'm somebody who tends to make a point of raising these issues, and even I'm getting bored of hearing myself make these same questions every time. So if somebody else out there is willing to share the load, I think perhaps everybody would be grateful. So finally, I've been a little bit kind of down on the scientific method throughout the talk, largely because it's in the nature of my talk that I've been describing things where science has gone a bit wrong. But I'd just like to emphasize that, science has made obviously huge advances, and the reason why it's made these advances is that scientists and clinicians have had the rigor to question those conclusions, and so I'd like to finish by just paraphrasing Winston Churchill, who was initially talking about democracy, and so this paraphrase goes that science is the worst form of inquiry, except for all those other forms that have been tried from time to time. So if somebody tries to convince you to make a clinical decision or an understanding about the world, and it's not based on an endeavour which welcomes and is susceptible to rigorous inquiry, then I think we're all obviously best off being sceptical. And finally, I'd like to end up with a plug for a book which doesn't exist, but if this book did exist, I think we should all buy it, and it's the I Spy book of science, How Not to Do It. Thank you.